All right, so redox is the shortening, as Janae said. Redox is basically the shortening for reduction and oxidation. When we talk about redox reactions, we're basically going to have reduction and oxidation, or if we want to say oxidation and reduction. Now, these two goes hand in hand. If you have a chemical equation, you are going to have, if you have reduction, then you basically have oxidation. And so both of them will occur simultaneously in a redox reaction. Now, reduction, what exactly is reduction? What exactly is oxidation? You can look at it in four different ways. Four things you can zero in on to deal with oxidation reduction. All right. So one of which is oxygen. The other way we can look at it is in terms of hydrogen. The other way we can look at it is in terms of electrons. And finally, the fourth way we can deal with reduction and oxidation or redox reaction is in terms of oxidation state or oxidation number. Cool? So those are the four ways. We can deal with it in terms of oxygen. We can deal with it in terms of hydrogen. We can deal with it in terms of electrons. Or finally, we can deal with it in terms of oxidation state, the oxidation number. So back then, scientists usually capitalize on the fact of oxygen and hydrogen, but would have recognized that not all reactions actually having oxygen and hydrogen. So the real focus is technically the electrons. Um, One of the things is we know that reactions really occur in relation to those valence electrons that are there on an atom. Those are the one of the driving things of a reaction. Cool. So let's look at it in terms of oxidation. Oxidation, and we say a substance is oxidized if these are the four ways, and we're going to be linking it back to those. One, if it gains oxygen. Two, if it loses hydrogen. Three, if it loses electrons. And four, if the oxidation number increases. So those are the four ways. And as I said before, initially scientists would have linked it to substances gaining or losing hydrogen, oxygen, and then they would have recognized that we have to, not all equations, it was only limited to that. And then they recognized that it's more than just gaining and losing of hydrogen and oxygen, and started to think about or add in the fact that the electrons are things that we can check, and the fact that oxidation number, whether it increase or decrease, we can check that. Substance is reduced if. So what is it that we use? And again, we go back to the four concepts, the four main ideas. One, it loses oxygen, right? Two, it gains hydrogen. Three, it gains electrons. And four, the oxidation number decreases. So these are the four ways. So if a substance is reduced, it will basically lose oxygen, it will gain hydrogen, it will gain electron, and as I said, the final one is the oxidation number, the oxidation state of the element or the substance, or the element within the substance, right, will basically decrease. The thing about it, we have some things that we need to clear up and we can link it back. Your prerequisite knowledge should know that which one of the elements, we have two groups of elements. Can you identify the two groups of elements? What are the two groups of elements? If I am an element, I'm either a or a.
Is it
Is it
metal or
metal or
non-metal?
non-metal?
Definitely. So I'm either going to be a metal or a non-metal. And so going back to the old fact about bonding, we know that what is it that, everybody that is in group 1 to 6 to 7, rather, they are unstable. And to reach stability, they will either gain or lose electrons. And by doing so, they can even share electrons in terms of covalent bonding. But if we're looking at it in terms of ionic compounds, basically, are formed from ions. We know we have cations and anions. We know as well, or you should know, that metals, they are the ones that actually lose electrons. And so, majority of the time, if you're looking at a metal moving from an atom to an ion, they will be losing electron. And so metals will basically undergo oxidation. So take, for example, magnesium. Magnesium is in which group? Magnesium is in which group?
Metal?
Metal.
So magnesium is in group 2. And what does that say about magnesium? In terms of electrons, the valence electrons.
It
It
has
has
two
two
electrons on
electrons
its
on its
outer
outer
shell.
shell.
Beautiful. And so we know that we kind of limit and kind of just for studying, we said that group 1, 2, and 3, including aluminum and excluding boron. If you look at that little staircase that we talk about on the periodic table, all those elements would have basically be once they have 1, 2, or 3 electrons in their outer shell, we regard them as being metals. All right, that's a simple way. So we know there's a link between the valence and the group. So the amount of electrons that are in the valence shell, the valence electrons, it tells you the group. But we really want to get back to the fact that in order for magnesium to become stable, what magnesium will do is to lose those 2 electrons. And when it loses the 2 electrons, it becomes the ion. And that ion has a charge of a 2 plus. Now, when we speak about the oxidation number, when we talk about the oxidation number, we are now talking about having to write the charge in front of that compound. So one of the rules in terms of dealing with oxidation number, later on we'll look at it, is that the monoatomic ion, if you know the monoatomic ion, then the valency, it will basically help you to determine the oxidation number. So magnesium, the oxidation state or number of the ion would have been a +2. So all we're doing in reverse to deal with the oxidation number is to technically write the charge before the numeral. So ion, if I'm talking about the magnesium ion, I will say 2 plus. If I'm talking about the oxidation number, I'm going to be saying +2. So how did magnesium get to this 2 plus? It had to lose electron. And we know, going back to the concept of protons and electrons and neutrons, we know that magnesium would have had 12 protons, because that's the atomic number. Atoms are considered to be neutral. They don't have a charge because they have the same number of protons and the same number of electrons. And so really and truly, those charges are canceling out each other. So an atom of magnesium would have had 12 protons and it would also have 12 electrons. But when you go through the losing of those 2 electrons on the outer shell, you now recognize that magnesium would have basically have 2 less electrons than proton. And even going a further step back, when you look at the charge, a proton is positive and an electron is negative. So when the element loses an electron, it will basically become positive. It forms a positive ion. And that is something you should have learned when we look at the whole atomic structure and when we looked at ionic compounds and when we look at bonding. So technically, the loss of electron is basically oxidation. Now, as we said before, there are certain 4 ways we can identify when each of these is happening. So losing an electron or losing electrons, that's oxidation. Cool? And so we can also speak about the oxidation number. We said that for oxidation, the oxidation number, if I scroll back to the top, the oxidation number increases. We should see an increase. Now, later on, we're going to be looking at the rules, but we can talk about it here. Remember, I just said the magnesium atom has 12 electrons and 12 protons. So really and truly, those positive and negative charge, they are canceling out each other. And so the oxidation state of the magnesium atom is technically zero. There's no difference in terms of the charge, right? The oxidation state, when this magnesium gives up the electron to a nonmetal to basically to become stable to form an ionic compound, what you find, as we said, the charge now, the oxidation state becomes a +2. Now, even though I have my equal signs here, really and truly, these represent the reaction arrow. So just forgive me for that. So if you look closely, the oxidation state is moving from 0 to +2, which simply means that the oxidation number is doing what? What is happening to the oxidation number?
It increased.
It increases. And we say once the oxidation number of an element or a substance increases, then we know that represents oxidation. All right. Let's talk about a nonmetal. We're going to be using oxygen. Really and truly, we know that oxygen represents one of the 7 diatomic elements. Diatomic meaning when you see these atoms of this particular element, they're going to be bonded to another atom. So when you're writing them in an equation, you always have that subscript of 2. If you're not familiar with the diatomic elements, remember all the group 7. So your chlorine, your bromine, your iodine, your fluorine, along with your oxygen, hydrogen, and your nitrogen. Those are considered to be the diatomic elements. Now, if in any case these two atoms of oxygen decide to bond, if you bond them with another metal, even this magnesium basically decides to give they become stable by giving each oxygen atom 2 electrons each. We know that is in total of 4 electrons. But while we talk about that, we can revisit the groups. Which group is oxygen in? Which group is oxygen in?
Group 6.
Group 6. And so we know that hence it has 6 electrons on its outer shell. We would have recognized when you're talking about ionic bonding, again, to simplify things as a student, you can remember that elements in group 5, 6, and 7, they tend to gain electrons to become stable. So if I'm in group 5 and we talk about that octet rule, getting that 8 electrons on the outer shell, and bear in mind the total electrons, because we do have the concept of helium, who has their first shell as the outer shell, and so they have 2 electrons there. But outside of that, oxygen has 6 on the outer shell, and so what you find is that it's going to need 2 electrons. And going back, when we look at the concept of what's the atomic number for oxygen? What's the atomic number for oxygen? What's the atomic number for oxygen?
16.
No,
8. 8.
8. And so the atomic number represents the number of protons. And we just dealt with it in terms of magnesium. So when we zero in on a atom of oxygen, it will basically have 8 electrons along with 8 protons. Now, to become stable, it is capable of gaining 2 electrons. So when it gains that 2 electron, it gains something that is basically negative. And so that's why we see where the ions that are formed for nonmetals are actually negative. We call those anions. They're negative because we're getting more electrons. And so oxygen would have gained 2 more electrons. So now when you look at the ion, that anion of an oxygen has 10 electrons but 8 protons. And so you have 2 more electrons than proton, and that is what gives that 2 minus charge for the ion of oxygen. Now, as I said before, this ion is also considered monatomic, right? And so just as though you have 2 minus in terms of oxidation, the value would have been minus 2, negative 2. The oxidation number is negative 2 for the oxygen. Going back to this, even though I don't know if I mention it, and one of the things is the rule. I zeroed in on the magnesium and told you that the electrons and the protons are basically the same. It would be the same for the oxygen atoms. A matter of fact, the rule says if it is uncombined with another element, the oxidation number for that element is 0. So if oxygen is not bonded to another element, or magnesium is not bonded to another element or any element at all, they're by themselves in an equation, then their oxidation number is 0. So right here, this oxygen or these two oxygen atoms, they're bonded to each other because this is really a covalent compound, but they're not bonded to a different element. So the oxidation number is 0. And when we look at it, if we're reading it, and as I said before, these equal signs represent my arrow. The arrow from 0 to negative 2, what is happening to the oxidation number? What's happening to the oxidation number?
Sorry.
Does what?
It decreases.
So it's decreasing, or it decreased. Now, what is happening if the oxidation number is decreasing? We know that it is being reduced. Now, oftentimes, students ask me this question: why is it that something is gaining, so the element is gaining electron, yet still we're talking about it being decreasing? What it is gaining is actually negative. So the electrons are the ones that are basically being passed on to the oxygen, right? And so it is decreasing. Now, in chemistry, in Jamaican terms, overseas they may use a different term, but we are familiar with this jargon, oil rig. So we note that oxidation is loss of electron, right?
Yes,
Yes,
sir.
sir. While when we see reg, we say that reduction is gain of electrons. That's an easy way to remember it. And as we said, we basically sometimes CXC will technically zero in on this concept of losing or gaining electron. And majority of the time, they will also talk about the fact that you have the increase or decrease of the oxidation number. Cool? Now, if it is that your most of the questions they will want to ask you what is happening to the particular compound, or what is happening, is this compound reduced or is it oxidized, is it the reducing agent, oxidizing agent, is it losing electron, gaining electron, things like that. And so one way to basically narrow it down is to be able to assign oxidation number. So if you can calculate the oxidation number, right, you should be good in terms of using that knowledge to determine if a compound or a substance is being oxidized or reduced. And so do this, as I said before, there are some basic rules that you can follow. Rule number one, the oxidation number, and these don't have to go in this particular order, guys. The oxidation number of uncombined elements is 0, right? So as I said before, we did the example, magnesium not combined to anybody. So say for example, you're doing an acid and acid reacting with a metal. So if you have, don't want to use magnesium again, let me say calcium, calcium solid, reacting, give me an acid, give me an acid, provide me with an acid. All right, provide me with the acid. What was the acid we said?
Hydrochloric acid.
The hydrochloric acid. Now, again, I'm just using some equal signs from a reaction arrow. Now, just to even recap, we know when a metal, a reactive metal, reacts with an acid, we have the displacement reaction happening, because if you look at this and if you know anything about the reactivity series, we know that calcium is basically higher in the reactive series than hydrogen. And any element that is higher in the series is able to displace the element that is lower. So right here, calcium is going to basically kick off the hydrogen from the chlorine and takes its place. And we get calcium chloride being formed. Now, one of the reasons why I'm going through this is to really show you the connection in terms of acids and base and oxidation and reduction. Because sometimes students believe that even though we're doing the topics, they are not related, but they are, because we know right here and then we're going to be getting the, the hydrogen gas. And when we spoke a while ago, the first rule is that the oxidation number of an uncombined element is 0. So if I'm supposed to check this calcium, is basically the oxidation number is 0. And the other one that you should be able to relate to is this hydrogen over here. And earlier on, we spoke about the diatomic elements, and hydrogen is one of the diatomic elements. Just as how we said oxygen is a diatomic element. And so because it is not combined to another element, the oxidation state is also 0. So as we said, by applying the rule, we can look at compounds that are in a reaction and assign oxidation number, because we can now track to see if the oxidation number increase or decrease, right? So while we go along, we are going to be applying the rules, and we're going to see how it will help us to benefit to get to the concept of who is being oxidized, who is being reduced. There is a second rule, and as I said before, these rules are not in any particular order. It says hydrogen has an oxidation state of +1. There's an exception, except when it is bonded to a metal. If it is with potassium, if it's with calcium, you know, it's going to take an oxidation state of -1. Cool? So if we look here, we're seeing the concept of a hydrogen right here. So this hydrogen, it's not bonded to a metal. We know that it should be a +1. So great. A matter of fact, let me remove this and copy this and carry it down so that we can see basically what happened. So we said this hydrogen is now +1 based on that rule. Cool? Third, we have a third rule. It says oxygen has a oxidation state of -2. And there's an exception, except when it is in a peroxide. And the particular peroxide that you'll come across in your course is hydrogen peroxide, right? Hydrogen peroxide, and when that happens, it's actually a -1. So we see any oxygen? No, we're not able to use that rule with this equation. But if there was an oxygen, we can. So here, take for example, if we look at this, what's the name of this compound? We should know that this is magnesium oxide. The oxidation state of the the oxygen would have been a -2. And therefore, for two reasons. We soon talk about it. So the rule that speaks about it is 3. We have other rules that we can use to get to this. So we're continuing. So even though there isn't any oxygen in this equation currently, we would have been able to assign a -2 if there was. So 4, the oxidation state of a monoatomic ion is the same as its valency. We spoke about that earlier on. We spoke about that earlier on when we looked at magnesium. We said that really and truly magnesium is from group 2, so when it forms that ion. So if we look at ionic compound, so right here again, let me bring this one down. If we're really looking at this, we're seeing a monatomic ions because the chlorine right here, so we can deal with the calcium and the chlorine here. So right here, the
I'm
chlorine,
sorry, sir, but could you go back up a little bit, please?
all right, to right here.
Yes, yes, sir, to number 3.
So we said that oxygen has an oxidation state of -2, except when in a peroxide, we say in that case it's going to be a -1. So back to the fourth, we're seeing that this right here, the chlorine, the chloride ion is present. And we said that it's really a negative. And we would have known that the one is in front of it, but we don't say that. So we said negative. And so technically, the concept is it would have been a -1, right? And so we can do that for these ions. Once you know the ion, you know the oxidation number. So we're going to play around with it. So what would have been the oxidation number of the calcium right here? What is the oxidation number of the calcium? And we said that it's based on the valency. If you know the ion that the calcium become, if you know the group, you know the ion. If you know the atomic number, you know the electronic configuration, you can figure out. So we still can use that principle to get to it. Remember, for CXC, you're supposed to be familiar with the first 20 elements, right? So we should be able to work from there. So again, what is it for calcium? It's a calcium ion. Which group is calcium in?
Group 2.
So what is the calcium ion? If you know the charge of the ion, then all you need to do is to basically reflect and basically convert that charge, place it in front of the numeral. So calcium will form a 2+. It's a monoatomic ion, 2 plus ion, right? And so the oxidation state is a +2. Now, we also see the concept right here of the chlorine again. Now, bear in mind, each chlorine, even though we have 2 chlorine atoms, and we're going to be talking about a little rule right here, when we're dealing with writing the oxidation number for this type of thing, we normally use it for 1 atom. So a popular mistake students may do, because they know that they can use that to calculate, and we soon get into that, we can use it to calculate the oxidation number of unknown elements in our compound. But when you're writing, if you're asked to write, so if we're using to calculate, we would have said we'd have to combine these two oxidation number and we get a -2. But when you're writing, you're doing it for 1 atom, and each atom is actually a -1. Remember, we have some other rules, but we can talk about it right here. All the rules that we need to deal with this have been utilized, and so we have been successful in adding oxidation states to all the elements within the compounds that are in this reaction. The reactants are on the left hand side, and just like reading, we read from left to right. So when we take calcium, for example, we recognize that the oxidation number is moving from 0 to a +2. Now, the only way calcium can move from a 0 to a +2 is if calcium atom is losing electron. And we say to ourselves, what is losing an electron? What's that concept called? We go back to this thing right here that we discussed earlier on. We say oil rig. Oxidation is the loss of electrons. And so right away as a student, you're able to make the link that right here, the calcium is being oxidized. So calcium is being oxidized because it is losing 2 electrons. But wait, we don't have to stop there. The calcium oxidation state increased. It moved from a 0 to a +2. What is the concept of an increase in oxidation number? We should know that when an oxidation number increases, that is oxidation, right? So we know the calcium is being oxidized. When we look at the chlorine oxidation number doesn't change. So we know that it's not, the oxidation state remains -1. So we know it's neither being oxidized or reduced. But when we check the hydrogen, right, is basically a +1, and it is going back to the atom state. Why did this have a +1? For the hydrogen to have a +1, it would have meant that this hydrogen would have lost that 1 electron on its outer shell. If it is going back to the atom, then it is getting back that 1 electron. And we say to ourselves, what is gaining an electron? And then we make the reference going back up, rig. Reduction is the gain of electron. So right there, this hydrogen is being reduced. And we did say, how is it? Why is it that we're using the term reduce? Really and truly, when they say reduce, we're talking about that oxidation number, that state, because if you note, it is moving from a +1 to a 0. What is happening to the oxidation state? Going back to your number line, I am moving from +1 to 0, then I'm decreasing. So I am reducing. So reduction. As I said before, oxidation and reduction will happen simultaneously. And so once you have a situation where you have oxidation happening, then you must have reduction happening as well. So in this case, the calcium is being oxidized, and if you want to say the hydrochloric acid is being reduced. Cool. There are some other rules that we never touched on because of the nature of that equation. When we sum the oxidation states of the elements in a neutral compound, when we sum the oxidation states of the elements in a neutral compound, it should add up to 0. We're going to be doing some examples for this one. And we can even use back the, well, let me not use that. Let me use a different one. What's the name of this compound? I'm going to write another one as well. What's the name of the first compound?
Carbon monoxide.
Carbon monoxide. Remember, we have to have that prefix, the mono, right? And the second compound? Second compound, people? How are them there?
Carbon 2 monoxide.
What's the prefix for 2?
Sorry, I forgot.
Anybody? And so, as I said,
Dimonoxide.
dioxide.
Dioxide. Yes.
Dioxide. Remember, we learned it when we dealt with naming covalent compound. We said we use the name of the first element as how it is on the periodic table. So we say carbon. We change or utilize the IDE name for the second element. So instead of saying oxygen, we say oxide, right? And so we have to indicate using prefixes to the second or the first element. And in this case, we have 2 oxygen atoms. And so we use the prefix dioxide. So that's why the popular carbon dioxide. All right. As I said before, we're not supposed to allow ourselves to forget the knowledge that we gain from the different topics because it's carrying across prerequisite, utilizing it to deal with the questions when we come up. But that's not our focus. Our main focus is, the thing is, some elements, I don't know what happened to them. Some of them have a tendency to have a difference in their oxidation state when they're in different compounds. So don't take it for granted you have carbon here, and carbon is one of them. Sulfur is another one, and nitrogen is another one. Those three elements in particular, you have to be careful because they can change their oxidation state depending on the compound that they're in. So in carbon monoxide, we're going to use this concept. We're using this rule. So it says that if I am looking at a neutral compound, what is a neutral compound? It's a compound that you're not seeing any charge. You're not seeing a positive. You're not seeing a negative. So carbon monoxide, if it wasn't just for example, not a neutral compound, then you'll see a positive, you see a negative. We have those polyatomic ions that we have. So the nitrate and the sulfate, those aren't considered to be neutral because they have a charge. Cool? We say that when we add the oxidation state of these compounds, it should give me 0. The thing about this is that we have to use a little mathematical approach. And so sometimes students don't like it because it's a little algebra, right? And at the end of the day, what you find is this. When you apply that knowledge, you're good because you're not going to be getting the carbon dioxide right here like that. You're going to be getting the carbon dioxide in an equation, but you can still use the concept of working out the oxidation state because, as I said, if you can get it for the elements, you can track and see which one the oxidation number is actually increasing or decreasing, and then you know who is being oxidized, who is being reduced. So with no further ado, we're going in. So we know when we add them two here, when we add them, I'm supposed to get 0. The problem is, as we said, carbon. Usually we don't know that for carbon, but there's a rule that governs oxygen. Oxygen, the rule says that oxygen, unless it is with a peroxide, will always have a oxidation state of -2. And so more than one rules will help you to work and get to the oxidation number of an element that you have. The carbon right here is the one that we don't know. And usually when we don't know something in a math, we say it is X. So technically X plus that -2 should get you to 0. Now, I'm not your math teacher, but we can reason it out. Two unlike signs, we know that is a negative, right? We say equal to 0. Again, the real and truly, what we want to do is to get X by itself. And so if I have a -2, I add 2 equal to 0. The concept is what I do to one side of my equation, I have to do to the other side of the equation. So I have to add 2 here. And so X, which is representing carbon, oxidation number is a +2. And when you plug it in, +2 -2, when you add both of them, you're going to get a 0. So sometimes, unless CXC asks you to work it out, because you're going to be in the exam and you're moving fast, you really want to just get to find out. The question just asks you, which one is being oxidized, which one is being reduced. If you show this working, you can actually, if you're a math person, you can really just look at it and know, say, hey, here we are. This is a +2. Nothing is wrong with that. So unless the question asks you to show working for a particular example, I've seen them ask that in questions. So they underline or they just say, okay, what is the oxidation state of the carbon in carbon monoxide? Show working. Fine. It requires you to show working, you do that. If it is not the case, then you just do your little working in your head and you get to it. But what I'm trying to bring across is you can use the rules to obtain the oxidation number of the elements. So once you do that, you can then assign the oxidation state and then you can track. Let's go back to why we said that we have to be careful. So if I come down here and say, oh, me just deal with carbon monoxide and the carbon did a +2, so this must be a +2, right? That's not necessarily going to be the case. Not necessarily going to be the case. And so what we want to do is to work it out. So again, in this case, we notice we have to take into consideration that we have 2 oxygen, but it's the same thing. We start by saying, is this compound, is carbon dioxide a neutral compound? Yes, it's a neutral compound. And so when we add the oxidation numbers, it should equal to 0. So when we look right here, remember we're going to be calling carbon X plus. Now, in this case, the oxygen is a -2, as we said, once it's not bonded to a peroxide. But at the end of the day, we have 2 of them. Cool? And so it is 2 times the -2. We have the X, we have the plus. This is going to give me a -4 equal 0. Working that out, we know the signs are different. End up with -4 equal 0. We want to get X by itself, so X minus 4 plus 4 equal 0. Whatever we do to one side, we have to do to the other. So we have to add 4. This is X equal plus 4. So if you notice, in this case, the carbon is equal to +4, while up here, that very same carbon is equal to a +2. So we have to be careful not to think that, the oxidation state remain the same. So that's why we should be able to work them out. Some other things we can apply. We're going to be using this one. So nitrate, the nitrate ion. The nitrate ion is now a polyatomic ion. And the rule is, we're working with a polyatomic ion, when we add or when we sum the elements, it should equal to the charge. So it should equal to the charge on the ion. So when I sum these, what should it be equal to? It should equal to -1, because that is the charge of the ion. If it was a sulfate ion, SO4, 2 minus, it would be equal to -2. Same concept. We don't know nitrogen. As I said, carbon, nitrogen, sulfur, those are the 3 elements you want to keep your eyes on when dealing with them. They tend to change their oxidation state. And so we call in nitrogen X plus. We know oxygen is always 2, except with a peroxide, which it is not with in this case, or in a peroxide. And so again, we're working it out. X, we get, we can jump some steps now. We know that it is going to be -6 equal to -1. So again, we jump in some steps. X will be equal to -1 plus 6, right? And so X is equal to plus 5. So in this case, the nitrogen is a plus 5. And really and truly, if you do it, you get back the same answer. Nitrogen is a -5, sorry, a plus 5, my bad. Each of those oxygen is a -2. So we have -6. Then that should equal to -1. And so sometimes when you work it out, if you want to to ensure that you're on the right track, you can plug them in and check, right? And so that would basically sum up you adding or basically being able to assign oxidation number using the rules. So nitrogen, trying this again, we have this popular element, well, this compound called ammonia. So let's do this. Ammonia in this case is a neutral compound. And right away, maybe some persons are able to just look at this and know that, hey, nitrogen right here is a -3. If you're not able to do that, you can go back to the working. Work from what you know. This time we're not dealing with oxygen plus 1, right? And we have 3 of them. And we said this is a neutral compound, so it should be equal to 0. So 3 times that, right away, seeing that, equal 0. And to fast track, when we carry across, and when we do to both sides, we end up with x being -3. So here it is again, as I said before, nitrogen. Up here, the nitrogen was a plus 5. Right here, the nitrogen changes its oxidation state to a -3. And so these are some of the elements that you want to monitor when you basically have them in an equation. Cool? So try sulfur trioxide. Can you figure out the oxidation state of the sulfur in sulfur trioxide? And is it different for the sulfur in the sulfate ion? We're trying those two. Sulfur in the sulfur trioxide, sulfur in the sulfate ion.